Welcome back. In today's video, we're going to cover errors and uncertainties, not only in physics, but in any experimental science. So before I start talking about what an error is and what is uncertainty, I want to cover two concepts that are commonly mistaken for each other or not understood completely. Those concepts are precision and accuracy. So first, let me start with precision. Precision means that your measurements, when you do an experiment, are close to each other. They don't have much standard deviation, but they are close to each other. If you wanted to use the experiment of throwing darts into a target, you could say that you have very high precision if all of your darts land in the same place, even if that place is not the center, but they land very close together at some location of the target. The second term is called accuracy. Accuracy is when measurements are close to the expected value or to where you wanted them to land. So in the example of throwing darts to target, then your experiment would be highly accurate if all of the darts land very close to the center, to the bullseye, or if they land all around it and on average, their average location is the bullseye. So you can have experiments that are precise but inaccurate, accurate but unprecise, or not accurate, not precise, or both accurate and precise. So let's see how that looks like in a scientific context. So for example, when you're doing an experiment, you usually have an independent variable and a dependent variable. You take data and then you graph it. If your independent variable and dependent variable have a linear relationship, your data points should approximately show a straight line going upwards, like in this example. For an example, let's use the physics equation x equals vt, which means that there's the displacement of an object is given by its constant speed multiplied by the time that it travels that speed. So in a graph, we would put the independent variable t over here and the dependent variable x over here. This line has a slope of speed v, since it's the distance over the time in this graph. So if we were going to do this experiment with a simulator that gave perfect results and no errors or uncertainties, we would expect that all the values would fall exactly on the line. So if we take data, for example, every, 8 data points, we would expect them to go something like this. All of them at equal intervals, exactly on the line, with no mistakes and no errors. Okay? So that's how it would look with a simulation. However, real experimental science always has sources of error, sources of uncertainty, which can affect the precision and the accuracy of your results. So let's see with 4 graphs how it would look if your experiment was not accurate and not precise, not accurate but precise, accurate but not precise, or accurate and precise. So first one, not accurate and not precise. Not accurate means that your points were not close to the line where we want them to be, and not precise means that they're not close to each other, that the deviation is very big from one to the other. So it might look something like this. You have points above and below the line. You have points before and after. You have higher points. Maybe you have more points up here, but also another one here, another one here. It just doesn't make sense. Your data is all over the place, and it's not clear from looking at it that there's a linear relationship between the variables. So this data means that we need to fix our experiment and do it again. Now, we can have not accurate but precise results. What would that look like? So that would be still maybe a linear relationship, but not on the line that we want it to be. So we might get some results like this. So it's pretty clear that the data is linear, but if we were asked to draw the line of best fit, it would be a line with a slope much lower than the slope that we were expecting. So this is precise. The data looks close together, but it's not accurate. It's not giving us the value of the speed that we were supposed to get. Now we can have data that is not precise but is accurate. That would mean that the data is spread throughout the graph, but it's accurate enough that if you were to take some averages, you would get the right amount of speed. So something like this. So this one would be too high, but then the next one might be too low, another low one, but then another high one, and maybe another low one, and another high one. So they're not perfect. They are a little bit separated, and they should be closer to the line, but they are accurate because they are showing a linear tendency with the exact slope of the line that we were expecting. And finally, we can have accurate and precise results. It would look very similar to theoretical results. However, since there's always some amount of uncertainty or error in our measurements, there would still be a little bit of distance from the points to the lines. So it might look something like this. Maybe this one, maybe one is perfect, but then this one is a little bit higher, lower, and then almost there. Yeah, so some small deviation from the expected line, but not enough, and that would be a good experiment. Okay, so now that we know this, I'm going to tell you a little bit about names of the different errors and how they affect the precision and accuracy of an experiment. Okay, so we have two types of error that we can get while taking experimental data. We could either get systematic errors or random errors, or both. So systematic errors are those that move all your data to a different value, but almost all of the data points are moved by the same amount. So it would be something like having your line not start at 0 but at 10, but then everything else would be exactly the same. So we can say that in systematic errors, the variation is the same every single trial. That means that the probable cause for that variation is that a device, a measuring tool, is probably not set up correctly. So for example, if I have a scale and I'm measuring different masses, but when no one's on top of it, the scale marks 10 kilograms. Well, if I measure the mass of everyone in the room, I'm going to get all of the masses too high by exactly 10 kilograms. So what happens is, if I do many trials, like hundreds of trials, but I don't look at the scale and see if there's something wrong, then I will never be able to take away the systematic error. The data will always consistently be 10 kilograms above what it should be. So this type of error, systematic errors, are not improved by taking repeated data or multiple trials. But this is not going to affect the precision of the experiment, because if our scale is very precise, it will still give us very exact numbers, just not close to the numbers that we should be getting. So an experiment done with a lot of systematic error will be inaccurate. So it leads to inaccuracy or not having accurate results. So how can we fix systematic errors? We need to check our tools, check our devices, make sure they give 0 when they're not measuring anything, make sure we start the timer at the same time, that the scales are correct. It's more about manipulation and fixing the tools that we're using to measure. There's another type of mistake called random error. As its name suggests, the variation is not the same anymore, but it's random and unpredictable in every trial. In this case, it does get better if you take multiple trials. Because if you only take one trial, you don't know if your data that you took is higher or lower than the average. However, if you take 20 times the same measurement, then some of them will be too high, some of them will be too low, and on average, they will cancel each other out until they get to the expected value. So in this case, multiple trials are an improvement. When we have random error, it doesn't affect our accuracy because we could still be getting very close to the expected value on average, but in an imprecise way. That means the data might be too scattered and you might need a lot of measurements in order to get a real result. So this is called unprecise. So in summary, if you want an experiment to be accurate, you need to decrease the amount of systematic errors that you have. And if you want your experiment to be precise, you want to decrease the amount of random errors that you have. How can you do that? By checking your devices before you start taking measurements, and by always making sure you take multiple trials. You can also take advantage of tools and devices that are more precise. That means that they give you more information, more significant figures in the reading, and we're going to get to that right now. Okay, so we already covered errors, which are sources of mistakes that can come up in your data that you want to diminish as much as possible so that they don't affect the validity of your results. But now let's talk about uncertainty. Every single measurement that we make has an uncertainty. Uncertainty means how much you can't be sure that your value is correct. So when you state a value with an uncertainty, you will always say, I think my value is probably this plus or minus this other thing, this uncertainty. That means that you're giving a range of values that your experiment has provided for you, and not just a single value. So the first thing that you need to take into account when you talk about uncertainty is the absolute uncertainty. We have three types of uncertainties: absolute, relative, and percentage uncertainty. Let's start with absolute uncertainty. Absolute uncertainty is the uncertainty that already comes in measuring devices. Every single thing that we use to measure is never 100% precise, but it has certain uncertainty. How do we measure and how do we give that uncertainty? By looking at how the device presents the data. So we have two types of devices that we use to measure in experiments. We have digital and we have analog devices. So let's start with analog devices. An example of an analog device is a ruler. A ruler has markings and it has units. So let's see what that would look like. So suppose I bought a ruler and it only has 3 marks. It has a mark at 0 centimeters, another mark at 5 centimeters, and another mark at 10 centimeters. So if I want to use this ruler to measure something, for example, my marker, I'm going to put it here, and I know for certain that the length of the marker is between 5 and 10 centimeters, but I'm not sure by how much. So I try to get as close as I can. This is probably less than 7.5. It could be like, let's say 6.8 would be my guess. The length of the marker would be 6.8 centimeters. But is it exactly 6.8? Can I really say that it's 6.8 without a doubt? I can't. I can say even less that it measures 6.81 centimeters, and even less that it measures 6.813500 centimeters, because that means I would know all of these significant figures and that the ruler gave them to me. But this ruler doesn't give enough information to make that point. So what I have to look at is the ruler and say, my length could be this, but it can also be between 2 values. So I'm going to add and subtract from that a set amount so that it gives me my range. So how does that work? When I have an analog measuring tool, you always want to get the smallest possible measurement that is for sure, and then divide it by 2. So here the smallest possible measurement is 5 centimeters, because I can get 5 centimeters here or 5 centimeters here. So like the distance between 2 adjacent lines. In this case, 5 centimeters. And then divide it by 2. So 5 divided by 2 is 2.5 centimeters. That means that my length is this. 6.813500 centimeters plus or minus 2.5 centimeters. This is true, but it doesn't make sense to have all of these numbers over here if I'm not even sure if it's about 4.3 or about 9.3. Yeah? So these numbers make no sense. How many of them make no sense? Well, actually, you should always have the same number of decimal places after the decimal point in this one and in this one. So if this one reaches only 0.5, so like one number after the decimal point, I can only use one number after the decimal point here as well. That means I'm going to ignore the 1, the 3, 5, the 0, and the 0. So my real answer is that my length is equal to 6.8 plus or minus 2.5 centimeters. This is how we would express a number and its uncertainty in a scientific document. However, if you think it's useful, we can also find the range. What does this mean? Well, this actually means if we do 6.8 plus 2.5, we're going to get 9.3. And if we do 6.8 minus 2.5, we're going to get 4.3. That means that we know that the length is in this range. It's between 4.3 and 9.3 centimeters. Notice that this range measures 5 centimeters. So what we're basically saying is we know that there's a 5 centimeter range where our value could be, but we think the most probable one, or the center of those 5 centimeters, is 6.8. Now, if my ruler was a lot better, and it gave me values every centimeter, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it gave me, even if they don't give me the numbers, but they give me the lines, and you know that the lines are exactly where the number would be, then I can measure my marker again, and I see that it's more than 6, but this time it looks like 6.5 actually. So now I would say that my length is 6.5. Plus or minus what? What is the amount of centimeters between two consecutive lines? Well, this time it's 1 centimeter. There's a line in 6, there's a line in 7, and there's a line in 8. So for every 1 centimeter, there's a line. So 1 centimeter divided by 2, that means my uncertainty would be 0.5 centimeters. Notice that I still can't add more numbers, more decimal numbers over here. I don't have enough information for that. But now my uncertainty is a lot smaller. Now I know that my range of possible lengths go from 6 to 7. There's actually 1 centimeter from my lowest guess to my highest guess. So the more precise my measuring device is, the more lines in a ruler, the more confident I can be that my answer is pretty close to the actual answer. So this is what happens with anything that is analog. So basically the rule for analog devices is, so plus or minus half of smallest distance between lines. Yeah, so the closer together the lines are, the more lines there are in a device, the more precise it's going to be to measure your results. Now that's for analog devices, any analog device with lines and marks. But let's go to digital devices. So an example of a digital device is a digital scale where you measure your weight that shows the numbers. In this case, let's say it's going to say 33 kilograms. So you measured your dog and it gave you 33 kilograms. So you're going to write your answer as the weight of my dog is 33 kilograms. How much is the uncertainty? Plus or minus what? Well, this time you're going to take the smallest possible value that your device can measure. So if it says 0 and you push a little bit and it still says 0, so you push a little bit harder, that minimum value that it shows is what you're going to take as your uncertainty. So in this case, it shows 33, so that means it can show 1. It doesn't have any decimal places or enough numbers to show decimal places, so the uncertainty will be 1 kilogram. Here, it would not make sense to write 33.0 because there is no point 0 or point anything after the 1. That means that we should leave it at 33. However, if your device were able to show and showed point 0, let's do that example. So 33.0. Let's see. So here, let's take a moment. Here, your range of values would be 33 minus 1, 32, until 33 plus 1, 34. So your weight, your dot's weight, is between 32 and 34 kilograms. In the case of 33.0 kilograms, the minimum weight that your scale can now show is 0.1, or well, 0.1. So that's what you're going to write as your uncertainty, 0.1, which is the same as 0.1 kilograms. That means that now your value is from 33.0 minus 0.1, which is 32.9, until 33.1. So notice that even though our value was the same, 33, 33.0, we consider that to be the same value. It's not, because it's much more precise if your digital scale gives you 33.0 than 33. Because if it says only 33, you could be between 32 and 34. But if it says 33.0, you know you're between 32.9 and 33.1. So there's only a range of 2 kilograms where you might be. So basically, to summarize this, so in analog devices, you add and subtract half of the smallest distance between lines, while in digital devices, you add and subtract the smallest possible number that you can read. So basically, if it says 33.578, then the smallest possible is 0.001. You go to the number most to the right, put a 1 there, and that's the number that you're going to use for your digital absolute uncertainty. So that's absolute uncertainty. Before I move on, I want to say a little bit of how we write this, notation. So usually, since algebra, you know that we call variables, we call them x. Any variable, we call it x. So for example, if I'm talking about this number over here, I'm going to call 6.5 my x, and the uncertainty, we call it delta x. Delta is a triangle. Delta is a Greek letter that means change in. So this would be x plus or minus change in x. That means that when I give a value, I also tell you how much I might change it to the right and to the left, how much I might subtract and add from it to get my real value. So taking that into account, I'm going to move on to relative uncertainties. Okay, so to explain relative uncertainties, I'm going to go back to what we just learned, that when we express a number, we say it is x plus or minus delta x. So the number plus or minus the uncertainty of that number. So this delta x is called the absolute uncertainty. The relative uncertainty would be delta x divided by x. It's going to give you a decimal number that says how big is the uncertainty with relation to the number. So it's different to say, for example, in this example, 33 plus or minus 1 kilogram, the uncertainty is 1. In this other example, the uncertainty is also 1. However, if I divide the uncertainty by the number, here I'm going to get 1 over 33, and here I'm going to get 1 over 0.003. You can do it in your calculator and you'll notice that this number is about 0.3. But this number is in the thousands. That means that even though we had the same absolute uncertainties, the relative uncertainty of the second number is humongous compared to the relative uncertainty of the first number. That means that our experimental results in the first experiment were much better than our experimental results in the second experiment. So the absolute uncertainty itself, 1 kilogram, doesn't say much. But it does say a lot when you relate it to the number that you wanted to find. So this experiment is very bad, this experiment is okay. We can also see that using percentage uncertainty. So percentage uncertainties are just another way to show the same relative uncertainties. You show them as a percentage instead of as a decimal. So it would look something like this. Delta x over x times 100%. So in this case, where it was a decimal of 0.03, in this case, if you would say it's about 3%. So if your percentage uncertainty is above 100%, your experiment is not very good. If it's close to 5, 10%, then it's a pretty good experiment. So basically, relative uncertainties and percentage uncertainties give you a way to compare different experiments with different units and different values and still know which one is more precise than the other one. So the smaller the percentage uncertainty, the more precise your experimental results. Now let's go to a part that can be a little bit more confusing, which is propagation of uncertainty.